Good morning, everyone. Today I'm really happy to introduce you Professor Dr. Edgardo Saucedo. Edgardo Saucedo's research career has been mostly devoted to develop novel photovoltaic materials, including copper, indium, gallium selenide, 6 solar cells, kesterites, novel two-dimensional materials that we hope will explain us today. And also he has been strongly involved in the optoelectronic characterization. He received his PhD in materials physics at the Universitat Autònoma de Madrid in 2007. And after that, he joined the French Institute, Institut de Recherche et Développement sur l'énergie photovoltaïque, IRDEP, with a CNRS Associate Researcher Fellowship. Professor Edgardo has a very rich background because he also has experience in the private sector, where in 2009 he joined an ICMAB spin-off company created from the Research Institute. He worked in Paris in order to pursue the training in photovoltaic technology. From 2010 to 2020, he was the deputy head of the Solar Energy Materials and System Groups at IREC, and last year became professor and researcher at the Universitat Politècnica de Catalunya. Edgardo has an outstanding CV, as you had the opportunity to see at his bio. He has coordinated many European projects, worth mentioning an ITN, ERC Consolidator Grant, and last year was awarded with the prestigious ASEBA Toyota Award for his contribution to the development of sustainable photovoltaic technologies using vacuum technologies. So, Edgardo.
Thank you very much, Mariona. I will remove my mask, sorry. And thank you very much, Mariona, for this very kind introduction. So, as Mariona told you, I'm Edgardo Saucedo, and I work in the photovoltaic group at UPC. So regarding my institution, we are 2 labs very connected and working together. One of the labs is dedicated to crystalline silicon solar cell. Joaquim Puidoyer, that is the head of the group, of the photovoltaic group at UPC, is here with us. And it's in the campus north of UPC, in the mountains, towards the mountains of Barcelona. And this is the new campus of UPC in Besòs, in Sant Adrià del Besòs. And in this campus, we have this new emerging thin field photovoltaic materials. So we are working together in almost all aspects, or even combining crystalline silicon solar cells with these emerging thin field photovoltaic materials, for example, tandem solar cell concept. These are 2 groups that actually are 1 group, but this is the people that used to work mainly at Campus North and with crystalline silicon solar cells and with new selective contacts as well that we are using a lot in our emerging thin field photovoltaic materials. And this is the new group at Campus Besòs. So basically, in terms of facilities at UPC Campus North, we have a clean room for the production of high efficiency crystalline silicon solar cells, but also for the production of many different selective contacts based on oxides, most of them, but also using organic molecules as well, or with dipoles for enhancing the selectivity of the back contacts, of all the contacts. And in Campus Besòs, this is really very brand new lab. We received the lab 1 week ago. So we're starting to put all inside, but these are images of all the new labs that are located here in the 4th floor, the entire 4th floor of this building. And we have 4 labs in one. So this lab is dedicated to the synthesis and characterization of emerging thin field photovoltaic materials, mainly chalcogenides, halides, and also some mixed chalco halides. So we have a laboratory for optoelectronic characterization of solar cell. We have a laboratory for thermal treatment. We have a laboratory for chemical processes and another for physical vapor deposition processes. So the main objective of this laboratory is to develop new materials for the photovoltaic community. And the good thing we have is that we can build the complete solar cell in our installations. This is the outline of my talk. I will just very briefly present Customart project because my presentation is mainly dedicated to a type of material called kesterite, and Customart is our current European project that is dedicated to develop kesterite towards the industrialization. So I will show you the characteristics and challenge of kesterite, and I will speak about two issues that are very relevant, I think, in most of the thin film photovoltaic technologies, that are doping and alloying strategies, and how in the past year, following these strategies, we discovered many things about kesterite, and we were able to develop this material towards the industrialization. Then I will present what we have beyond kesterite, the new materials that we are starting to investigate. And finally, I will give some conclusion and perspective. So starting with the Customart project, this is a very large project, around 7 million euros. We are 20 partners all around Europe. And we were coordinating previously 2 European projects, a scarce cell and a kesterite cell that develops all the fundamental aspects of kesterite. So we demonstrate that the technology can be useful for some photovoltaic applications, mainly in building integration and building adapted photovoltaic concept. So in this project, we are joining several industries around Europe, trying to produce a first prototype of a product with kesterite. I will speak a bit more and will explain you a bit more following this, why kesterite, what is the relevance of kesterite or the interest of kesterite that can have at industrial level. So for the introduction, why we need kesterite, why we are working after 10 years in this really complicated material, because for thin film technologies, we have 2 beautiful technologies, copper indium gallium diselenide and catalurite. In this very famous efficiency chart of NREL, you can see that copper indium gallium diselenide and catalurite have efficiencies even closer to the crystalline silicon technology. So this means that these 2 technologies are already at industrial level. You can buy 6 uncatalyzed solar modules in the market. You can buy easily and are also complementing crystalline silicon very well. Nevertheless, these 2 technologies have a big issue. They contain indium and gallium in the case of copper indium gallium diselenide, and tellurium in the case of catalurite. And of course, cadmium is a toxic element. But indium, gallium, and tellurium are identified by the European Commission as critical raw materials. This means that sustain a very large industry producing copper indium gallium selenide and catalurite is almost impossible for Europe, because there is not enough indium, gallium, and tellurium in the market to sustain a very big production with these 2 technologies. So time ago, some scientists start to think about possible replacement of these materials for materials that are abundant in the earth crust, and of course with low toxicity and sustainable. And in this sense, 2 years ago, a group of scientists, we start to compile these emerging technologies in this paper. So for the ones that are working on photovoltaic, probably you are aware and you know very well the photovoltaic efficiency tables of progress in photovoltaic. So we are doing similar thing with IOP, with the Institute of Physics in United Kingdom, compiling all the emerging materials, the record efficiency, the progresses yearly. And this is very nice input for knowing which materials are at the forefront of the research for the scientific community. In particular, if you take a look to this paper, you will see that several kesterite type materials are really at the forefront with the highest efficiency and with many different systems under intensive research. This is the second version of this paper with updated efficiencies, updated materials, and so on. And now we are starting to work in a third edition that will be even more extended than this. And we are starting to invite other authors to contribute as well. So, given the importance of kesterite, what are the characteristics of this material that made this kesterite very interesting for photovoltaic application? First, if you take a look to the structure, this structure is a tetragonal structure. It's very related to the copper indium gallium diselenide structure, and is very related to the catalurite structure, and at the end, very related to the silicon structure. Basically, if in the silicon structure you take two atoms, one silicon replaced by cadmium and the other for tellurium, you form the zinc blend structure that is the catalurite structure. Then if in catalurite you substitute one cadmium for one copper and one indium and one tellurium for one sulfur or selenium, you have copper indium selenide or sulfide that is a tetragonal structure, but is also very related to catalurite. And in kesterite, what we did is to take the indium and substitute two indium by one tin and one zinc. And then you have the kesterite structure. The normal kesterite structure, you have copper tin planes and copper zinc planes, and in between the chalcogen planes in the structure. Being very related with catalurite, copper indium gallium selenide, and silicon from the structural point of view implies that we know many things about this material. And this material, for example, is fully compatible with any copper indium gallium diselenide production line. So a company producing copper indium gallium diselenide can very easily shift to kesterite or produce both together if necessary. In addition, the material is exclusively formed by low toxicity and earth abundant elements, exhibits naturally p-type conductivity that is quite easy to control. Also, most of the different alloy exhibit direct band gap, and in the region that is of interest for photovoltaic application between 0.8, 0.9, up to 2 electron volts if you want, or even more. And highly compatible with SiC technology. This makes this material kind of the dream for a photovoltaic researcher or even for a material researcher. But of course, nothing is perfect. And the beauty of this structure that is very flexible in the point of view of design of material and design of devices is also the nightmare of this material. Why? Because first, you can note here that copper and zinc are in the same plane or share the same structural plane. And copper and zinc are structurally identical, are isoelectronic elements. So an exchange of copper and zinc in this plane is very easy from the thermodynamic point of view. And this introduces disorder in the material and can introduce defects that kill the photovoltaic properties of your material. In addition, tin tends to form volatile species with the chalcogen, with selenium and sulfur. So the control of tin in this structure is very complex, extremely complex. Tin, in addition, is a multivalent element. So you can have tin plus 2, tin plus 4, or even in this solid state structure, tin plus 3 or something like that can be also possible. So this kind of multivalent element tend to form defects in the band gap. Normally, these defects are detrimental for the solar cell performance. In addition, we found some years ago that tin strongly interact with alkaline elements, and I will show you that alkaline elements are really of vital importance in this technology. And this is an additional complication and very different what happens with the CZTS. Finally, zinc is the less problematic of all of them, and sometimes can be volatile, but normally you don't have any problem with zinc, excepting this copper and zinc exchange. So all these problems of kesterite, all the defects introduced by copper and zinc exchange by tin due to all these characteristics of things, hamper the improvement of the voltage of kesterite. So this technology suffers from a quite high voltage deficit. And this is the main problem that we are tackling currently, and we are facing currently, and we are trying to solve. After several years of discussion, because of course we know that we have a VOC deficit, this VOC deficit was identified as really related to the non-radiative recombination of the material used to exhibit quite low photoluminescence, indicating that we have quite a lot non-radiative recombination. And after several years of research and also theoretical research, we found that most probably all the tin-related defects are at the origin of this non-radiative recombination and this VOC problem of the material. Currently, we believe that tin on zinc is the main problem, and we should find ways, strategies to try to avoid this defect that is quite complex to avoid. And all the tin-related defects used to be giant recombination traps and can be the origin of this VOC deficit. So right now we are investigating about this possible tin on zinc defects to improve our kesterite. But how to try to reduce the concentration of this defect or avoid the presence of these defects? One possibility is to go towards zinc-rich conditions. So our material is copper 2, tin, zinc, tin 1, zinc 1, selenium 4, for example, in a stoichiometric condition. But if you prepare a zinc-rich compound with, for example, copper 2, tin 1, zinc 1.2, selenium 4, then you can try to avoid the formation of this kind of thing. The problem is that when you increase the zinc concentration and you are going toward out of stoichiometric condition, zinc selenide and zinc sulfide tends to be formed, are very stable phases, and normally also deteriorate the properties of your devices. Another possibility is to produce tin-po compound, but this implies that normally copper-rich secondary phases are produced and are very conductive, and this really kills your material. So the tin-poor compound doesn't work at all. The other possibility is to have a whole poor N-type material forming kind of this kind of acceptors. But normally this is uncontrolled and you cannot work with whole pool N-type condition. Thermodynamically, it's very difficult. And also in addition, in the thin film community, we are very good doing solar cells with P-type absorbers, but we are extremely bad doing with N-type absorber. So normally with an N-type absorber, we don't know how to prepare an efficient solar cell. All the thin film solar cell, the absorber, the heart of the solar cell is a P-type semiconductor. So the possible solutions we are investigating. First is the partial substitution of tin by germanium. Germanium is a more novel material in the sense that normally the defects are less detrimental, at least from theoretical investigation, and higher efficiencies were also theoretically predicted. The second is doping with hydrogen, basically inspired by 3,5 semiconductors. In them, the doping with hydrogen normally removes free electrons and reduces recombination. And I will show you last results about all this doping and alloying on kesterite. These are just two examples. And why we think this is the solution or can really have a high impact on kesterite? Because if we take a look to the close cousin copper indium gallium diselenide, time ago, CZTS was at 12–13% efficiency. And the jump in efficiency was thanks to two processes developed for CZTS. So if we take a look to the copper indium diselenide and kesterite with band gap around 1 electron volt, efficiencies are not so different. The same for 1.5. Nevertheless, in this region that is the most interesting one for photovoltaic application, the difference is very high. And to go from 12–13% efficiency up to more than 20%, what CZTS adopted was doping process and alloying process. Doping with alkaline elements and alloying with gallium. Copper indium diselenide alloyed with gallium is a much better semiconductor than copper indium diselenide by itself. Then, inspired by CZTS, that is a very related material, we think that doping and alloying can be the key processes that can help to improve the efficiency. What we know about doping and alloying up to now on kesterite, in this paper, you can find a very nice review about almost everything on doping and alloying on kesterite. And if you take a look to the periodic table, you will see that most of the elements that have worked very well with kesterite are the alkaline elements. Okay, and this is quite similar to CZTS. Then we started to work with these alkaline elements. Alkaline elements play different role on kesterite. I won't like to extend too much because it will require hours to explain alkaline in this system, but basically what alkalines do is first to improve the crystallization, but because you used to form crystallization fluxes with sodium and selenium, then the temperature required for a very nice crystallization of the material is much lower than normal. And the second helps to control the conductivity of the material. For example, for sodium, the theory is that when you synthesize your material at high temperature, sodium occupies copper position. Then when you cool down your material, this sodium is not soluble anymore in your solid, and then migrate toward the grain boundaries. And then keep a copper vacancy. And these copper vacancies are the ones that control the p-type conductivity. So the use of this alkaline is really very important for controlling the conductivity of your material. We thought that same will happen with kesterite, and in some extent, yes, but several groups working on that more or less at the same time, where this alkaline doping start to be a hot topic on kesterite, report differences. For some of them, sodium was the best alkaline to dope, for some other potassium, for some other lithium, and so on and so on. There was a discrepancy in this scientific community about which alkaline is the best for kesterite. And in one of the European projects, we discovered that this is because alkaline interact with tin. So here you can have something like the tin concentration on kesterite, and here the different alkalines in different quantities. Then you can see that the lithium achieved the maximum efficiency for 33% of tin. Nevertheless, sodium for 31, and potassium for 29, and rubidium for 27. Then, depending on the alkaline element you are using, the tin content to maximize your efficiency has to be tuned, and it's very different. And this explained why, for depending if you are working on this condition, sodium is the best doping for you. If you are working in this tin concentration, potassium is the best for you. If you are working with this tin concentration, lithium is the best for you. This was a very nice discovery, and after that, lithium demonstrated to be the best one. But surprisingly, lithium is very similar to hydrogen. So then we start to suspect that maybe lithium is not only affecting the kesterite by forming copper vacancies and improving the conductivity. Could be also lithium play a role like hydrogen to passivate all these free electrons? So we are starting to work on that, and we have evidences that this is real on kesterite, because doping with hydrogen is very complex. Doping with lithium is much easier for us. Some months ago, basically, a Chinese group reported a new world record on kesterite working with lithium. They use lithium bisfluorosulfonyl imide in the precursor, and they demonstrate a very nice effect on kesterite. And then with this, they were able to produce a new world record with this material. In this paper, that is a very nice and interesting paper, they say that mainly lithium is acting as a crystallization flux, improving the crystalline quality of the material and having perfect grains on kesterite. And this is the reason for the improvement. I don't think that this is the only reason for lithium. We have evidences that also lithium is playing a more important role in kesterite, or an additional role to those. This is true, okay, but there is an additional effect of lithium. So to demonstrate it, we think that lithium have some similar effect than hydrogen. So we decide to design experiments using this kind of compounds: sodium boron hydride and lithium aluminium hydride. During the formation of kesterite, this is the thermal treatment you need to synthesize and crystallize kesterite. Normally, you have to go up to 550, where the material reacts, is synthesized and crystallized. So what we do is, during these synthesis processes, we include in the atmosphere these hydrides, and we study the effect on the kesterite properties. Basically, these hydrides tend to decompose at different temperature, giving the free elements, including hydrogen, lithium, and sodium. And we have a very nice surprise with this, because we observe that in some cases, working with lithium, we have a really huge improvement in the VOC of the material. Also, the other properties are boosted, including the efficiency, of course, but mainly the VOC, that this is the most complicated one to improve. In particular, the use of sodium boron hydride doesn't lead to any remarkable improvement. This is mainly because we think that there's too much sodium in the system for kesterite. So we are trying to adapt and see if sodium boron hydride can be usable. But for the moment, using this in the atmosphere, this introduces too much sodium and then deteriorate kesterite, because you need some given quantity. If it's too much, then you start to have a lot of problem in your material. But lithium aluminium hydride led to a general improvement of all these optoelectronic parameters. And this here, collaborating with Helmholtz Zentrum Berlin, we observed that the quasi-Fermi level splitting of the material, including lithium in the atmosphere, improves a lot. And this is an indication that we are reducing the recombination, the non-radiative recombination of the material. And it's probably the first direct proof that the lithium can help to reduce this recombination on kesterite. So this confirmed that the small atom dopings of kesterite can be extremely relevant in the future to further improve this record efficiency. So the other element that was very relevant for doping was germanium and tin position. Then in that sense, my former group in IREC, we worked a lot and we reported most of the papers regarding this. These are two examples of papers we published on germanium doping, and we observe a large improvement of the efficiency when germanium is included in the system. It's really almost double the efficiency. And we produced time ago the first record of copper, zinc, tin, selenite in the world by substituting germanium. This was another evidence that germanium is the problematic one. So now we are trying to work with a combination of germanium and lithium that is not so easy to do, but we are working on that to see if we can have both positive effects. Then, about extrinsic doping, up to now, lithium and germanium are the most promising one, and something wrong happened with tin, and then to understand and solve the problem related to tin defects, maybe with germanium and lithium, I think is one of the most interesting strategies to follow in the future. To go faster, so now I will jump to alloying, because another possibility is to start to change drastically to material, not just with doping that you are adding tiny quantities of material. Here we will change drastically the material, substituting large quantities of each element in your structure. And so in that case, this is the basic structure of kesterite: copper, zinc, tin, sulfur, selenide. And then you can substitute copper by lithium and silver, zinc by manganese and cadmium, tin by germanium. And these are the main elements that have been investigated. I will go fast through these because I think that is the details are not so important at all, just the conclusion. First substitution was lithium, and lithium shows once again that up to 10% you have a large improvement of efficiency and VOC. The problem is that then for higher lithium quantities, the efficiency drops. And normally it's because the formation of secondary phases related to lithium. So it seems that you can use lithium for alloying, but only up to 7% efficiency. And in that case, the system after that is much more complex and is not useful to go towards higher lithium concentration. Silver gives very interesting properties to copper, because when you add silver, normally silver is much bigger to copper, then this copper-zinc exchange is not easily from the thermodynamic point of view anymore. And then silver tends to go to the right position and not exchange easily with the zinc. This reduces the possible copper-zinc disorder. But even with this, the efficiencies obtained up to now are not so high, and this is because there is a problem. Silver tends to change the conductivity of kesterite, so convert kesterite into an N-type material. And as I told you before, we are very bad doing devices with N-type material. Even though it was proved that you can alloy with silver in a large extent, and if in the future someone solved the problem to build a decent device with silver, can be a solution also for kesterite. Although silver is an expensive and non-abundant element. So I don't think for proving something, it's okay in the lab, but not for the future development at industrial level. Manganese also at the beginning gives some nice results substituting zinc, but they basically were for very tiny quantities of manganese. So the people normally right now doesn't work anymore on manganese. This is just to show you how many things we tried in the past in order to consolidate the technology that most of us, we are working right now. Cadmium also substitutes zinc and can reduce the disorder in the material. This was already proved, and this gives very nice reason. And in particular, cadmium, for example, improved the microstructure of the kesterite, reduced the band tailing problem because substitute zinc, and then this disorder is not anymore possible, increase the minority carrier lifetime, and then improve the efficiency. Then substituting zinc by cadmium and the kesterite is also a possible technological solution in the future. And using this, another world record was reported for this compound that is formed by copper, cadmium, zinc, tin sulfide, normally around 20% of cadmium. Finally, for germanium, there are many works on germanium, and in all of them, the efficiencies are very good normally. So when you start to substitute germanium, by germanium, up to 40% of substitution, you can achieve very nice efficiencies, more than 12%, quite or relatively easily, indicating once again that tin is a problematic material. Once again, germanium is a quite expensive and non-abundant element. So to solve problems, to understand problems is very nice, but we need to go back to the tin always, because tin is the really abundant element. So all this work are very useful for understanding the properties of the material, but not for industrialization in the future. And as a bonus, recently some groups start to work in co-doping, in double cationic substitution, for example, using cadmium and silver with very interesting results. We are now working in double substitution with germanium and lithium, trying to also improve the properties of this material. As a summary, all these possible elements and even much more have been proved for kesterite. And the most promising doping elements are lithium, sodium, and germanium, and alloying are cadmium and germanium. Maybe combination of them can give very nice surprises in the future. But for the moment, these are the defects on kesterite that are always eating our previous work. And after several years, we don't have real progresses on efficiency. Let's hope that in the future, our new ideas will really eat at this defect on kesterite and we can achieve efficiencies going beyond 20%. So what we have beyond kesterite to finish? So once again, in this Journal of Physics material, you can find that most of the emerging thin film photovoltaic materials can be classified in 4 types: oxides, nactides, chalcogenides, and halides. And basically, if you take a look to the structure, to all the possible structures of the material, most of the good performing photovoltaic material in the past were cubic or tetragonal. But currently, more and more, most of them, of the new materials, are having disordered system, like orthorhombic, hexagonal, and monoclinic system with non-tetrahedrally bonded elements. So several of them are anisotropic material, low-dimensional material that in the past we thought that this type of structure can never produce a decent solar cell, but currently we are demonstrating that all this structure can produce very nice solar cells and have very interesting properties. Among all the materials under research, you can see chalcogenides are so far the most abundant one, and here you have examples of all the materials that are under research, most of them inspired by kesterite, some oxides, some nactides, and quite a lot of halides. And this is increasing, and mainly is increasing the combination of chalcogenides and halides. This is a summary of the progress depending on the type of material, and once again, you can see that chalcogenides and halides are the most interesting one for the moment and reporting the highest efficiency. And maybe a mix of them can be extremely interesting in the future. And this is start kind of non-cubic or tetragonal inorganic materials revolution, because we become really for the first time very relevant for the photovoltaic community. And in this sense, 2 years ago, I was granted with a ERC consolidator grant to develop a system of materials, of a family of material with low dimensionality for solar harvesting, but mainly for photovoltaic material. What are these materials? Most of them are impaired in antimony selenide or antimony selenide, are kind of quasi one-dimensional absorbers. The characteristic of this material is that they have a very strong covalent bonding in one direction, in 2 directions, sorry, and then you form ribbons. And then these ribbons are bonded among them with van der Waals energy, so very soft energy. So you can use all these van der Waals space to dope the material, to put nanoparticles, to give the material special properties. For example, 1 year ago, more or less, we proved that putting selenium here, we can convert this material in this direction in almost an insulating material. And we improve a lot the fill factor of our devices, just putting here selenium, blocking the current in this direction, and increasing the parallel resistance of our devices. So in this project, for the next 4 or 5 years, we will investigate mainly chalcogenides, halides, and mixed chalco-halide of germanium, tin, antimony, and bismuth. And we are combining this with all the technologies developed and the ideas that we develop at Campus North in terms of selective contacts, using this combination of oxide with dipolar molecules to simplify the structure of these devices, and also to adapt much better our selective contact to the properties of these new quasi one-dimensional materials. For conclusion and perspective, in kesterite. So I think that we demonstrate in the last year that alkaline doping is a key issue for kesterite. And germanium also is a very interesting doping element. In terms of alloying, germanium, lithium, and cadmium are the most versatile ones for the moment. And that every time we touch tin, we tend to improve something on tin, and we succeed, we have an improvement in efficiency. In my opinion, tin is our nightmare right now. And for the moment, we cannot substitute it for nothing. So we need to understand what is really wrong and we think is this kind of tin on zinc defect, and how to solve this problem technologically. And beyond kesterite, we can classify the materials in oxide, knactite, chalcogenide, and allied. And among them, I think that peroxide allied and anisotropic chalcogenide are at the forefront for the moment. And that bit by bit, we are going towards non-cubic and non-tetragonal materials. And we start to observe that can be really beautiful materials with really incredible properties, and sometimes even better than symmetric or isotropic materials. Finally, I would like to acknowledge the European Commission for the funding for all this research, Mariona for this very, very nice invitation, and all my colleagues at UPC and my former colleagues in IREX. And thank you very much for your attention.
Thanks, Edgardo, for this beautiful talk. Is there any question in the audience? For those who are connected online, you can write down your comments in the chat that you will find at the bottom of your screen.
Sorry to go very fast with alloying and doping with not many detail, but it was the idea to present what we are doing on kesterite. If you would like to know more details about the fundamental science behind all this doping and alloying, I'm very open for discussion right now, or even you can contact me by email.
Okay, sure. If not, I will start. I have a couple of questions. One regards the material manipulation. It was in slide 22, I think.
I think the numbers are very wrong.
Yeah, a bit crazy, but it was at 22 there.
Copying and pasting from
when you are talking about the lithium and this one. Okay. So how easy is to work with these compounds? Because I'm aware that they are quite explosives, and so I don't know how. Do you need to work in the glove box? Is enough to work in the glove box?
Can be dangerous, really, but we are working with very tiny quantities. And we are putting 20 milligrams of these elements. And normally we used to prepare ES in a glove box. So normally the process for synthesizing kesterite is you deposit in a glass substrate coated with molybdenum, copper, zinc, and tin. Elemental copper, elemental tin, and elemental zinc, using sputtering or using evaporation of the metals. When you have this precursor that are only the metal, you put it in a graphite box, in a semi-closed graphite box. And in the graphite box, you introduce your chalcogen, sulfur or selenium, and a mix of both, and then these compounds, if you want. And then it's introduced in a tubular furnace where you perform your thermal routine to synthesize and crystalline kesterite. So in the system, you already have only 20 milligrams of this material in a very big system.
Okay.
So from this point of view, it's not dangerous. Are hygroscopic, mainly lithium aluminum hydride, and can be explosive. So we normally used to work in a glove box with them with these tiny quantities, even for safety reasons as well.
Okay, understood. Okay, and one more question regarding the kesterite devices. When you build a device, you use...
Yeah, because I didn't explain at all the structure of the kesterite device.
Yeah, if you can briefly mention the...
Okay, I can here use this to explain. Sorry for not explaining the device structure, but normally, you know, in a solar cell, you need your absorber material, so your photoactive material, and two selective contacts, one for electrons and one for holes. So the typical kesterite structure, we use soda lime glass as substrate, very cheap substrate. Then molybdenum is the back contact. And we are very lucky because when you synthesize kesterite, in the way I explained it before, using a selenium or a sulfur atmosphere, naturally molybdenum selenide or molybdenum sulfide is formed. And this is a very nice selective hole transport layer, selective contact for holes, and it's formed naturally in the compound. It's the same in CZTS. So in that sense, we were very lucky with this. Basically, for CZTS, there is no other back contact than molybdenum that works well. Okay. So we need to use molybdenum first because fulfill all the properties to be a very good back contact, but also because molybdenum selenide or molybdenum sulfide is naturally formed, and you can have here a whole selective contact. Then you have your absorber that is always a p-type material, and then we use as electron selective contact n-type cadmium sulfide. Okay. And then we finish our devices with zinc oxide and ITO as a top contact, transparent top contact. And we illuminate our devices this way. So this contact on top, cat sulfide, intrinsic zinc oxide, and ITO are transparent to the light.
Okay, thank you very much.
You're welcome.
Yes, we have a question from Salman Ali. If you can unmute your microphone and proceed.
Can you hear me?
Yes.
Yeah.
Just I had was generic question. As we see that recently, organic semiconductor based and the perovskite material based solar cells are really like say gaining attention. So what do you see like say the future of conventional inorganic semiconductors and the other type of like the organic and perovskite? So what do you think in future, where are we going?
In terms of S2, SB2, SAE3, sorry, because it's a bit hard to hear you. So
so can I repeat it?
If possible, in short.
Okay, I'm saying like recently the perovskite and organic semiconductors are like say gaining much attention also in solar cells.
Yeah.
And like say as we know the well-known inorganic like silicon-based material are like say that are like say well-established material for solar cells. So in future, what like say where we can see the organic, perovskite, and the silicon-based solar cells?
Okay, in terms of organic or hybrid solar cells, I'm not expert on nothing, but of course in hybrid solar cells or organic is not my field of expertise. I think that hybrid perovskite are beautiful materials demonstrating extremely high efficiencies, are really very nice. The main problem is still the durability of the material, so are unstable material. And you know, for a photovoltaic material, you need to demonstrate 30 years duration under operation. And perovskite are extremely far for that. So even if efficiencies are very nice, they have to demonstrate that can withstand 30 years of operation, like silicon, like CZTS, or like telluride that have demonstrated so far more.
Yeah, thank you very much.
In terms of this, inorganic perovskite are very interesting and reporting very nice efficiency as well. Okay, but cesium is a very expensive element as well. And then these are very nice from the research point of view, but for industrialization of this compound is extremely complex because cesium is extremely expensive. And they are not so stable at all. The new materials, this one, at least antimony is in the limit, but is not considered critical. So we can work with this. In terms of stability, for the moment, we don't have any evidence that the material is not stable, seems to be stable. What we found that these interfaces can be unstable because the material, as I explained, you are ribbons with van der Waals interspace. So once you put a contacting material, if you hit a bit, elements from your contacting material can easily diffuse from this van der Waals region. And normally we observe deterioration of the conducting elements. If we use capsule 5, for example, the solar cells start to evolve quickly. So in some week, you start to observe that the device change with it, and normally is deteriorated. And we have demonstrated also is because the sulfur diffusion toward the antimony selenide. This new kind of selective contact that are mainly oxides, extremely stables, I think can withstand much better and can solve this problem. We are really working on this new kind of more stable contacts for this system in order to stop this problematic interface instability.
Okay, thank you for your question. We have another question here in the chat from Pamela Machado. Pamela asks, is it easy to control the thickness of the MOSE2 layer that is naturally formed?
It's not easy, but it's possible. And the way we control it is, I think, from the technological point of view, very elegant. So basically, let me go. So we are not using one molybdenum layer. I will go. Okay, thank you. I'm sorry. I think the way we use is very elegant, sorry. Actually, we don't have a single molybdenum layer here. We have 3 layers. So we have a first molybdenum layer that is extremely conductive. It's a very good conductor, but reacts very fast with selenium and sulfur. Then we use a second molybdenum layer that is grown under lower pressure, higher pressure, and then contains oxygen. And is very resilient towards sulfur and selenium atmosphere. It's not very good conductor, but it's very resilient and protects the conductive one below. And then we use a sacrificial layer on top. We put again a very good conductive molybdenum layer we call sacrificial layer that react with selenium and sulfur, forming the desired molybdenum selenide thickness. Normally we use 50 nanometer of this molybdenum sacrificial layer to form 150 nanometer of molybdenum selenide that is enough as selective contact. And the molybdenum here that we grow under high pressure protect and stop the selenization.
We have another question on the room.
Thanks for this presentation. It seems to me that you at the beginning you have discussed the properties and the problem, let's say, of the kesterite.
Yeah.
And then in the final part of your presentation, you moved to a kind of two-dimensional materials.
Yeah.
So I'm wondering, how do you see the future of the kesterite? Why have you moved to the 2D? Do you think that the problems that you have emphasized with the kesterite can be solved? Or are problems really related to the intrinsic nature of the material, which is a very complex structure, 2 different layers are understood where very similar elements should be there and should be ordered, and it's always very difficult. So anti-sides are going to be always very frequent. Yeah. So do you think that there is a way to overcome these difficulties or not? And why have you moved to the 2D?
This is my question after several years as well. I'm trying to answer myself first. I don't think kesterite will achieve 25% like silicon or CZTS, but for some applications, it's not required. So what we are developing now is some applications and prototypes that can use kesterite, that can use a lot of kesterite, and with efficiencies of 12–15% is more than enough. And in terms of price, because it's very cheap material, it's also possible to have a technology and to develop some products using kesterite. Of course, kesterite will never substitute silicon, I think you will never see a farm of kesterite modules in the world, nothing like that. But for building integration application, building adapted application where you can do flexible things, when you can do semi-transparent things, some things that for silicon are extremely complex, I think kesterite can have some market and application in our cities. For this, our estimations in a custom art project is with 15% is more than enough to be competitive.
And in terms of endurance of the device?
Kesterite is a natural material. You can mine kesterite. So if you can find kesterite in the nature, imply that it's extremely stable. It's an extremely stable material. It's a material that is synthesized at a high temperature. In that sense, it's the same as SAGES and catalurite. And why to open to new materials? You know, we are researchers, so we are looking always for something new. So I was working on kesterite after 10 years. So at this moment, so the kind of things that we can do with kesterite start to be saturated, and we need new ideas, new materials that can, for example, right now, tandem solar cell is becoming extremely relevant because you can go to 40% efficiency maybe in the future. And this antimony selenide and antimony sulfide are extremely interesting for that because you can produce it at relatively low temperature, at 300, 320 degrees, and then make it much more compatible with silicon than other inorganic technologies.
Thank you.
For such applications are extremely interesting.
Any further questions? Do we have any other questions on the chat?
Actually, you have to know that there is one company in Europe producing kesterite modules. So you can buy a kesterite module.
Okay, if there are no further questions or comments, we will close the talk here. Thank you once again, Edgardo, for being here and explaining us all this kesterite work to us. Thank you very much.
Thank you very much, Mariana, to you. And thank you to all of you.